to Starry Cosmos. Imagine a single beam of light traveling for an entire day. It would circle Earth more than 7 times, reach the moon and back twice, over yet still feel contained. Now picture something launched from our world nearly half a century ago, relentlessly outward bound, slowly extending that beam's reach. In late 2026, Voyager 1 will quietly cross a threshold, one light day distant from Earth, an unprecedented distance for any object built by human hands. This isn't about speed or even destination, but the sheer scale of what this small probe represents. A tiny emissary tracing an unimaginable path through the cosmos and revealing just how much empty space truly exists between us and everything else. If these quiet journeys through space help you unwind, take a moment to like this video and subscribe to the channel. It genuinely helps more dreamers find their way here. So dim your lights, settle in, get yourself comfortable, let your breathing slow, and let us begin. If these quiet journeys help you drift off, take a slow breath and subscribe to Starry Cosmos so the next one finds you when you need it. Imagine for a moment the late summer of 1977. The world felt different then, brimming with a cautious optimism. The Vietnam War had recently ended, leaving a deep scar, but also space, literal and figurative, for new dreams to take hold. Star Wars was about to explode onto cinema screens, capturing our collective imagination with tales of galactic adventure. While on Earth, the hunt for practical progress continued apace. Microcomputers were beginning their slow creep into homes and offices, promising a revolution in how we lived and worked. But it still felt distant, almost fantastical to many. It was an era defined by both a weariness with past conflicts and a burgeoning hope for the future, a desire to look outward and upward instead of inward and back. And that is precisely what happened on September 5th of that year, from Launch Complex 39 at Kennedy Space Center in Florida. Bathed in the warm glow of the setting sun, Voyager 1 began its journey. It wasn't an instantaneous burst of flame. It was a careful, deliberate unfolding, a testament to years of meticulous engineering and unwavering dedication. The Titan E rocket, a workhorse of its time, slowly but surely lifted Voyager, along with its twin spacecraft, Voyager 2, launched just weeks before, toward the vastness above. You might picture plumes of smoke and roaring engines, but it was more subtle than that, a controlled power building steadily until gravity finally relinquished its hold. The initial mission wasn't to reach interstellar space, not to become an ambassador for humanity to the cosmos, though those possibilities were certainly considered. The primary objective, remarkably focused at the outset, was a grand tour of the outer planets Jupiter and Saturn. These gas giants, shrouded in mystery and swirling with unseen forces, held the keys to understanding the formation of our solar system, the origins of Earth itself. Scientists wanted to map their magnetic fields, analyze their atmospheric compositions, and photograph their moons in unprecedented detail. It was an ambitious undertaking, pushing the boundaries of technology and demanding a level of precision never before attempted. Before Voyager 1 even cleared the atmosphere, it carried with it more than just cameras and scientific instruments. It held a message, a carefully curated collection of sounds, images, and greetings intended for any intelligent life that might one day intercept it. This was the golden record, an ambitious and profoundly hopeful undertaking spearheaded by astronomer Carl Sagan and his team. Think about the audacity of that endeavor. To encapsulate the essence of humanity, its joys, sorrows, triumphs, and frailties, onto a single gold-plated disc, barely 12 inches across, then cast it out into the cosmic ocean, with no guarantee it would ever be found. The record wasn't simply a random assortment of human achievements. Every element was chosen with deliberate care. Greetings in 55 different languages, from common tongues like English and Mandarin to less widely spoken dialects, offered a chorus of voices representing the diversity of our species. Sounds of earth, wind, rain, birdsong, whale calls, the rumble of a volcano were included to convey the sense of a living planet teeming with life. Musical selections spanned cultures and eras, from Bach and Beethoven to Chuck Berry and traditional music from around the world. Photographs depicted scenes of everyday life, landscapes, portraits of people, and scientific diagrams intended to explain our place in the universe. It was an attempt at self-portraiture on a cosmic scale, a message in a bottle cast out into the deep. And it wasn't just about what we wanted to say. Sagan and his team carefully considered how another civilization might interpret the record, anticipating potential misunderstandings and cultural biases. The design itself was meant to be universally understandable, relying on mathematical and physical principles that would presumably hold true regardless of where or who discovered it. Instructions for playing the record were etched onto its cover, using a symbolic language based on binary code, and fundamental constants like pi, concepts thought to be shared by any technologically advanced civilization. Think about the sheer optimism embedded in that project, even during the Cold War, at a time when humanity seemed perpetually teetering on the brink of self-destruction, there was still this unwavering belief in the power of communication, in the possibility of connection with something beyond ourselves. It wasn't just about seeking extraterrestrial life. It was about celebrating what it means to be alive, to experience beauty, wonder, and complexity. The golden record is a reminder that even amidst our differences, we are all part of a single, fragile tapestry of existence, adrift on a tiny pale blue dot in the vastness of space. Voyager 1's initial encounter with Jupiter in March 1979 provided more than enough data to justify this incredible undertaking. The spacecraft revealed swirling storms larger than Earth and discovered active volcanoes on Io, one of Jupiter's many moons. It was a revelation, rewriting textbooks and challenging established theories about the nature of these distant worlds. Saturn followed in November 1980, its majestic rings unveiled with breathtaking clarity and detail. Those images, the delicate bands of ice and rock shimmering in the sunlight, became iconic symbols of space exploration, inspiring generations to look up and dream. But even as Voyager 1 completed its planetary mission, its journey was far from over. As the spacecraft continued onward, propelled by gravity assists from the planets it had visited, scientists realized that it might actually escape the confines of our solar system entirely. And that is what has happened, unfolding slowly but inexorably over the decades since. It's a testament to the ingenuity of its creators and the resilience of its design, built to withstand the rigors of space travel. Voyager 1 continues to transmit data back to Earth even today, nearly 49 years after launch. And now, in November of 2026, we stand on the cusp of another milestone, a moment when Voyager 1 will officially cross the threshold of one light day from our home world after launch. And now, in November of 2026, we stand on the cusp of another milestone, a moment when Voyager 1 will officially cross the threshold of one light day from our home world. But to truly appreciate that distance, to grasp what it means for a signal to take an entire day simply traveling back to us, let's rewind nearly 50 years and trace the path that brought this tiny emissary so far. Imagine, if you will, the Earth receding beneath Voyager as it climbed away on its Atlas Centaur rocket, a pillar of fire pushing against gravity's hold, carrying with it not just instruments and technology, but a message, a portrait of our world sent outward into the vastness. The initial thrust carried Voyager beyond lunar orbit quickly enough, but to reach those outer planets, Jupiter, Saturn, Uranus, Neptune, and then beyond, required something more than sheer power. It needed finesse, a cosmic dance, utilizing the gravitational pull of other worlds. The first steps of this intricate choreography took Voyager on a close approach to Venus in December of 1977, just months after launch. This wasn't about studying Venus itself at that stage, though valuable data was collected regarding its dense atmosphere and swirling cloud cover. It was primarily a gravity assist maneuver. Think of it as a gentle nudge, a carefully timed swing past the planet as Voyager fell into Venus's gravitational well. The planet's own motion imparted some of its momentum to the probe, effectively slingshotting it onward with increased velocity. It's like a skilled billiard player using the cue ball to send another caroming across the table, gaining speed and changing direction in the process. From Venus, Voyager continued on toward Mars, arriving in March of 1978. Again, this wasn't a dedicated Martian mission. Orbiters were already in place, studying the red planet, but rather another opportunity for gravitational assistance and, crucially, an early calibration exercise for its suite of instruments. The close flyby allowed engineers on Earth to fine-tune the cameras, spectrometers, and magnetometers, ensuring they were functioning optimally before encountering the more distant and complex environments around the gas giants. Picture the careful adjustments being made thousands of miles away, tweaking settings based on the data streaming back across interplanetary space, preparing for the challenges ahead. The reddish hues of Mars filled Voyager's field of view, a tantalizing glimpse of another world before it pushed further out into the darkness. These early encounters weren't just about speed and calibration, though they were also opportunities to test the probe's ability to withstand the harsh realities of deep space, the extreme temperatures, the intense radiation, the constant bombardment of micrometeoroids. Every successful maneuver, every bit of data received was a confirmation that Voyager was built to endure. The instruments weren't just measuring planets. They were measuring themselves, proving their resilience and longevity in an environment utterly hostile to life as we know it. Once clear of Mars, Voyager embarked on the long leg of its journey toward Jupiter, a grand tour through the inner solar system, culminating in encounters with the behemoths of our family of worlds. That first swing past Venus added approximately 16,000 miles per hour to Voyager's speed, a substantial increase. The Mars encounter provided another boost, though less pronounced. It wasn't simply about accumulating velocity. It was understanding how these gravitational interactions altered the probe's trajectory, allowing mission controllers precisely aim for its subsequent targets. Imagine tracing that path on a star chart. A carefully plotted course, weaving between planets, utilizing their movements like stepping stones across the solar system. It requires an astonishing degree of precision, accounting not only for the positions and velocities of the planets, but also for the subtle effects of gravity from countless other bodies, asteroids, moons, even the sun itself. Each calculation had to be perfect, each maneuver executed flawlessly, or Voyager would miss its targets and drift into the void. The initial data collected during these flybys helped scientists build a more complete picture of Venus's volcanic surface, hidden beneath its perpetual cloud cover, and refined our understanding of Mars' atmospheric composition and geological features. Even those brief encounters added significantly to our knowledge, but it was the promise of what lay ahead. The swirling storms of Jupiter, the majestic rings of Saturn, that truly drove Voyager onward. As Voyager left the inner solar system behind, speeding away from the warming glow of the sun, it entered a region increasingly dominated by the solar wind, a constant stream of charged particles emanating from our star. This outflow exerted a pressure on the spacecraft, and understanding its effects was crucial for maintaining the probe's orientation and power supply. The instruments continued to operate, even as they traveled through ever-decreasing levels of sunlight, gathering data about the interplanetary medium, cosmic rays, and magnetic fields. And all this happened while constantly transmitting back information across millions of miles. It's easy to forget that Voyager wasn't just a passive observer. It was an active participant in a conversation across vast distances, a beacon of human curiosity, venturing into the unknown. Each signal sent back to Earth took minutes, even hours, to arrive, creating a strange and ethereal dialogue with our distant probe. By the time Mission Control received confirmation of a successful maneuver, Voyager had already moved millions of miles further along its path. It's a reminder that communication across interstellar space isn't instantaneous. It's a slow, deliberate exchange, demanding patience and ingenuity on both sides. The calibration data collected during those initial encounters with Venus and Mars helped to make sure every signal sent across the darkness would be clear enough for us all to hear. And with those checks complete, Voyager's trajectory aimed towards something truly immense. Jupiter. Even now, imagining that approach feels almost overwhelming. A small emissary of humanity venturing into the domain of a gas giant so vast it could contain over 1,300 Earths. It wasn't merely passing by. It was an intimate inspection, a series of carefully calculated flybys designed to unlock secrets hidden within the Jovian system for decades, even centuries. As Voyager drew closer, the swirling tapestry of Jupiter's atmosphere began to resolve into breathtaking detail, revealing structures we hadn't fully grasped from Earth-based telescopes. Of course, we knew about the Great Red Spot, that persistent anticyclonic storm easily visible, even through modest instruments. But Voyager didn't simply confirm its existence. It unveiled its complexity. The swirling cloud formations weren't static, but dynamic, constantly evolving within a well-defined oval shape. It was far larger than previously estimated, large enough to swallow Earth whole several times over, and possessed winds that raged at incredible speeds, exceeding 250 miles per hour, with no sign of diminishing. Studying the red spot wasn't just about observing a storm. It was about understanding atmospheric dynamics on a scale we hadn't encountered before, principles that might apply not only to Jupiter, but to gas giants throughout the galaxy. The swirling bands around the planet became clearer too, revealing intricate patterns and subtle color variations, indicating differences in cloud composition and altitude, all hinting at the sheer power of convection driving these immense weather systems. But it wasn't just Jupiter itself that captivated scientists. Its moons proved equally fascinating, each a world unto itself, with unique characteristics begging to be understood. The Galilean moons, Io, Europa, Ganymede, and Callisto, had been known for centuries, observed by Galileo himself with his rudimentary telescope. But Voyager's close flybys revealed details previously unimaginable, and no discovery was more startling than what it found on Io. For a long time, Io was thought to be a geologically dead world, a barren rock orbiting its giant planet. What Voyager showed us was anything but. The images beamed back were astonishing. A surface covered not in craters like most moons, but in vibrant colors, yellows, oranges, reds, and pockmarked with hundreds of active volcanoes. Plumes of sulfur dioxide erupted hundreds of miles into space, painting the landscape with volcanic ash and lava flows. It was an otherworldly spectacle, evidence of intense tidal heating caused by Jupiter's immense gravity stretching and squeezing Io, generating internal friction and fueling these spectacular eruptions. This wasn't a quiet, frozen moon. It was the most volcanically active world in our solar system, and its discovery revolutionized our understanding of planetary geology. suggesting that geological activity isn't solely dependent on distance from the sun or internal heat left over from formation. Io proved that tidal forces could be powerful enough to drive ongoing volcanic processes for billions of years. Then there was Europa, a moon cloaked in an almost unsettling smoothness. Its surface appeared strikingly free of impact craters compared to other moons in the Jovian system, suggesting it had been resurfaced relatively recently. This smooth, icy shell created a captivating mystery. The images revealed a network of dark lines crisscrossing its surface, long, linear features that at first seemed like cracks or ridges. But as Voyager gathered more data, scientists began to suspect something far more extraordinary. These weren't simply geological formations. They were evidence of a vast ocean lurking beneath the icy crust. The idea was radical at the time, but it made sense considering Europa's orbital characteristics and the gravitational influence of Jupiter and its other moons. The tidal forces that fueled Io's volcanism also flexed Europa, generating heat within its interior and potentially preventing an ocean from freezing solid. Voyager couldn't confirm the existence of this subsurface ocean directly, but the evidence was compelling enough to spark decades of further research, fueling missions like Europa Clipper, designed specifically to investigate this promising world for signs of habitability. Think about that. A moon orbiting Jupiter, shielded by a thick layer of ice, potentially harboring more water than all of Earth's oceans combined. A place where, against the odds, life as we know it might just exist. The Voyager encounter with Jupiter wasn't simply a flyby. It was a turning point in our exploration of the outer solar system. It transformed our understanding of gas giants, volcanic moons, and the potential for subsurface oceans. The data collected during those few intense days dramatically expanded the boundaries of what we thought was possible, revealing worlds far more dynamic and complex than anyone had imagined. Voyager moved on after that encounter, continuing its journey outward, but it carried with it a wealth of knowledge gained from Jupiter's realm, reshaping our perspective on the universe and preparing us for the grander mysteries still to come. It continued further still, pushing ever onward into the darkness between the stars, carrying with it not just instruments and data, but also the hopes and curiosity of humanity itself. And as it journeyed outwards, it edged closer to a milestone that had seemed impossible when we first set it on its path, crossing the threshold of one light day from Earth. And as it journeyed outwards, it edged closer to a milestone that had seemed impossible when we first set it on its path, crossing the threshold of one light day from Earth, but long before Voyager reached that distant marker. Well back in the early 1980s, it brushed past another world of almost unimaginable beauty. Saturn, perhaps no other planet in our solar system, presents such a striking visual spectacle as this gas giant, and certainly none with rings quite like its own. Consider for a moment how much we take for granted when we gaze at those familiar arcs painted across the night sky, that what appears so solid, so defined, is actually composed of countless particles of ice and rock, ranging in size from specks of dust to mountains larger than some cities on Earth. Voyager's approach to Saturn allowed us to see these rings with a clarity previously unavailable, revealing their intricate structure for the very first time. Before its arrival, we knew of the broad divisions, what we call the A, B, and C rings, but the resolution from even our most powerful telescopes was limited. Voyager showed us that each division wasn't simply empty space, but rather contained thousands upon thousands of ringlets, delicately woven together in a complex tapestry. Imagine slowly circling Saturn, approaching those rings at tens of thousands of miles per hour. The light reflecting off the ice particles would become increasingly brilliant until finally they resolve into individual pieces, glittering against the black void. You'd quickly realize these aren't perfectly uniform bands. They ripple and wave, sculpted by the gravitational influence of Saturn's many moons. These shepherd moons, as we came to call them, orbit just inside or outside the rings, their gravity confining the particles and preventing them from spreading out. It's a kind of cosmic dance, a perpetual balancing act between attraction and repulsion. The challenge for Voyager's imaging team was considerable. The intense glare from Saturn itself, combined with the subtle contrast within the rings, made capturing detailed images difficult. They employed clever techniques, using filters to block certain wavelengths of light and carefully adjusting exposure times. But even then, processing those raw images required painstaking effort. What emerged were photographs that revealed a level of detail no one had ever imagined, showing spokes within the B ring, faint ripples caused by gravitational disturbances, and the complex interplay between different ring particles. But the rings weren't the only source of discovery around Saturn. As Voyager drew closer, it detected evidence of several new moons orbiting the planet. These small bodies, some just a few kilometers across, were hidden until Voyager's sensitive instruments could pick them out amidst the glare of Saturn and its larger satellites. Each new moon added added another piece to the puzzle of how this planetary system formed and evolved. We now know that Saturn has at least 83 confirmed moons, each with its own unique orbit and history. And then there was Titan, Saturn's largest moon, a world so peculiar it demanded even closer scrutiny. Unlike most other moons in our solar system, Titan possesses a dense atmosphere composed primarily of nitrogen, much like Earth's. However, instead of water clouds, Titan has clouds of methane and ethane, hydrocarbon compounds that rain down onto the surface. This created an environment vastly different from anything else we'd encountered. Scientists theorized for years about what lay beneath those hazy skies, a mystery Voyager could only partially resolve. To truly understand Titan, to pierce through its atmospheric veil, required sending something down to the surface, a concept that ultimately led to the Huygens probe, launched in 1997 as part of the Cassini-Huygens mission. This little lander detached from the orbiting spacecraft and descended through Titan's atmosphere on January 14th, 2005. It was an audacious undertaking, sending a fragile human artifact across billions of miles of space to parachute onto an alien world. For over 20 minutes, Huygens transmitted data back to Earth, revealing landscapes unlike any we'd seen before. Rounded pebbles sculpted by hydrocarbon rivers, vast plains carved by wind-blown sand, lakes and seas filled not with water, but with liquid methane and ethane. It was a glimpse into an alternate version of our own planet, a world where the chemistry is different, yet somehow familiar. The data from Huygens confirmed that Titan's surface wasn't frozen solid, as some had predicted, but rather a dynamic environment shaped by weather patterns and geological processes. Consider for a moment what it means to send such a probe into the unknown. Years of planning, meticulous engineering, countless simulations, all culminating in those few precious minutes of data transmission. The risk was enormous. There was no guarantee Huygens would survive the descent, or that its instruments would function properly. But the rewards were immeasurable. It expanded our understanding of planetary formation, atmospheric science, and the potential for life beyond Earth. Voyager didn't carry a lander like Huygens, but it laid much of the groundwork for such future missions. Its observations of Saturn's atmosphere, rings, and moons provided crucial information that guided the design of Cassini-Huygens and helped scientists interpret the data that probe returned. It demonstrated the power of robotic exploration to unlock the secrets of our solar system, to push the boundaries of human knowledge, and to inspire a sense of wonder about the vastness of space. The rings of Saturn witnessed by Voyager weren't just beautiful bands of light, they were glimpses into a complex, fascinating world that continues to captivate us today. And as Voyager continued its relentless journey outwards, it carried with it not only data and images, but also the hopes and dreams of humanity, a quiet testament to our enduring curiosity about the universe around us. Continued its relentless journey outwards. It carried with it not only data and images, but also the hopes and dreams of humanity, a quiet testament to our enduring curiosity about the universe around us. As Voyager passed beyond the orbit of Pluto, leaving behind the last vestiges of what we might call planetary space, something subtle began to shift. The familiar embrace of our sun, the light that nourishes life on Earth, the warmth that drives our weather systems, started to diminish in its influence, replaced by a growing sense of isolation and exposure. Imagine standing further and further from a comforting fire, feeling the chill creep in, even as the embers still glow faintly behind you. This was the experience of Voyager, venturing into the immense gulf between stars. For decades after launch, Voyager had been riding the solar wind, that constant stream of charged particles emanating from our sun. This wind creates a vast bubble around our solar system, known as the heliosphere, protecting everything within it from the harsher realities of interstellar space. But gradually, almost imperceptibly at first, this protective breeze began to weaken. The pressure exerted by the solar wind lessened as Voyager moved further away, encountering ever-decreasing densities of these energetic particles. It wasn't an abrupt transition, more like a gentle easing off, a gradual surrender of control. Picture yourself sailing against a strong current, then noticing that the current is beginning to slacken, allowing you to rely more on your own momentum and direction. This slowing of the solar wind was a key indicator that Voyager was approaching the edge of our sun's influence, a region known as the heliopause. The heliopause isn't a sharp boundary like a wall, but rather a turbulent mixing zone where the outward push of the solar wind finally balances against the inward pressure of interstellar space, a place where our sun's energy meets the broader galactic environment. It's a dynamic, shifting region, constantly fluctuating in response to changes in both the solar wind and the surrounding interstellar medium. Think of it like the shoreline during a particularly vigorous tide, sometimes receding, sometimes advancing, never quite holding a fixed position. As Voyager edged closer to this boundary, scientists began to notice an increase in galactic cosmic rays, high-energy particles originating from sources beyond our solar system, remnants of ancient supernova explosions and other cataclysmic events. These particles are always present in interstellar space, but normally the heliosphere deflects many of them, shielding the inner solar system from their potentially harmful effects. With the diminishing strength of the solar wind, however, this shield began to weaken, allowing more cosmic rays to penetrate inwards. It's a curious thought, isn't it, that as Voyager moved further away from our sun, it was simultaneously being bombarded by particles born in the violent deaths of stars long ago, remnants of cosmic events that unfolded across vast distances and eons of time. These aren't just random fragments hurtling through space. They carry with them information about the extreme conditions under which they were created, offering clues to understanding the life cycles of massive stars and the evolution of galaxies. Voyager's instruments became increasingly sensitive to these energetic particles, providing valuable data on their composition, energy levels, and direction of origin. The change wasn't merely a matter of numbers increasing on a graph. It was a fundamental shift in the environment surrounding the spacecraft. The nature of space itself seemed to transform, where once there was a relatively stable and predictable flow of particles dominated by our sun. Now there was a more chaotic and unpredictable sea of energy, teeming with cosmic debris from across the galaxy. Imagine swapping a tranquil lake for an open ocean, feeling the swell of waves beneath you and sensing the raw power of the elements. The heliopause itself proved to be surprisingly complex. Voyager wasn't simply crossing a line. It was navigating a region filled with magnetic fields, plasma waves, and turbulent eddies. The spacecraft encountered a series of fluctuating boundaries and density gradient as it moved through this transitional zone, like threading its way through a labyrinthine maze. Scientists spent years analyzing the data from Voyager, painstakingly piecing together the puzzle of how the heliosphere interacts with interstellar space. The transition wasn't instantaneous or clear-cut. It took time for the instruments to register a definitive change in conditions. Analyzing the fluctuations in plasma density and magnetic field strength provided the most compelling evidence that Voyager had finally crossed into interstellar space, the region beyond the reach of our sun's influence. Though definitions are still refined, the prevailing consensus amongst scientists now places the crossing around August 25th, 2012 for Voyager 1 and September 12th, 2013 for Voyager 2. With each passing hour, each additional mile traveled, Voyager was venturing further into the unknown. becoming a true interstellar explorer. It wasn't just reporting back on its findings. It was the finding, a physical manifestation of humanity's reach, extending beyond the boundaries of our solar system and into the vastness of the cosmos. And as sunlight dimmed to almost nothing, replaced by the faint glow of distant stars and the constant hum of galactic cosmic rays, Voyager continued onward, a tiny speck of metal and silicon, carrying with it the weight of human curiosity, hurtling through the darkness towards a future yet unwritten. The sun, once so dominant in its warmth and light, became just another star in the grand tapestry of the Milky Way, a distant beacon marking home as Voyager embarked upon a journey into truly interstellar solitude. And as Voyager relinquished its grip on direct solar influence, it entered a region unlike any spacecraft had known before, a vast buffer zone between our sun's domain and the true emptiness of interstellar space. This isn't an abrupt wall, not a clear dividing line, but a gradual transition, a slowing down, a stretching out of the solar wind as it meets resistance from the surrounding galaxy. We call this region the Heliosheath, and understanding its properties has been one of Voyager's greatest gifts to science. Imagine blowing bubbles into a gentle headwind. The air rushing past shapes the bubble, stretches it thin, diffuses its colors before it finally pops. That's a rough analogy for what happens at the edge of our solar system. The solar wind, an outflow of charged particles from the sun, is constantly streaming outwards, creating a bubble around us known as the heliosphere. But the galaxy isn't still. Stars move through space, and with them flows the interstellar medium, gas, dust, and magnetic fields. This flow interacts with the solar wind, compressing it on one side and stretching it out into a long tail on the other, shaping the Heliosheath like an enormous comet hurtling through the cosmos. For decades, scientists theorized about this region, predicting how the solar wind would behave as it slowed down and mingled with interstellar material. But theory can only take you so far. Voyager's instruments provided the first direct measurements, revealing a complexity that exceeded expectations. One of the primary ways Voyager charted its course through the Heliosheath was by measuring the temperature and density of the plasma, the superheated gas consisting of free electrons and ions surrounding it. As the spacecraft moved further out, the plasma grew hotter and denser, not because it was closer to the sun, but because it was being compressed by the incoming interstellar flow. This compression heated up the particles, increasing their kinetic energy and changing the properties of the solar wind itself. Consider that Voyager wasn't simply seeing this plasma. Its instruments were counting individual charged particles, determining their energies, and mapping their direction of travel. It's a painstaking process, akin to feeling your way through a dark room, relying on subtle changes in texture and temperature to build up a mental picture of the space around you. The readings revealed that the temperature within the Heliosheath wasn't uniform. It fluctuated significantly with distance, indicating turbulence and varying densities throughout this vast region. In some areas, Voyager detected localized hotspots where the plasma was particularly energetic, hinting at interactions between different interstellar flows. But measuring the plasma alone didn't tell the whole story. The magnetic field plays a crucial role in shaping the Heliosheath and guiding the flow of charged particles. As Voyager ventured further from the sun, it began to detect subtle but significant changes in the direction of the magnetic field lines. Close to the sun, these lines spiral outwards, neatly organized by the solar dynamo, the process that generates the sun's magnetic field. But within the Heliosheath, those neat spirals started to become more disordered, twisted, and tangled as they interacted with the interstellar magnetic field. Imagine stretching a rubber band and then twisting it along its length. The tidy parallel lines become warped and chaotic. That's what was happening to the solar magnetic field, distorted by the pressure from the surrounding galaxy. Voyager's magnetometer detected that the magnetic field gradually reoriented itself, shifting from pointing primarily outwards from the sun to becoming more aligned with the galactic magnetic field. This transition wasn't instantaneous. It occurred over a period of years. As Voyager traversed the outer reaches of the Heliosheath, this change in magnetic field direction had a profound effect on how charged particles moved through space. The magnetic field acts like an invisible highway, guiding these particles along its lines. As the field reoriented itself, so too did the paths of the energetic cosmic rays, high-speed particles originating from distant supernova and other cataclysmic events. Voyager observed that the intensity of galactic cosmic rays increased significantly as it entered the Heliosheath, because the weakened solar magnetic field offered less shielding against these incoming particles. This isn't just an abstract scientific observation. It has implications for understanding radiation exposure in space and the potential hazards to future astronauts venturing beyond Earth's protective bubble. The interactions between the solar wind, the interstellar medium, and the magnetic fields at the edge of our solar system aren't merely passive encounters. They create a dynamic environment where particles collide, accelerate, and radiate energy across the electromagnetic spectrum, generating radio waves, X-rays, and even visible light. Voyager detected these emissions, providing further clues about the complex processes occurring in the Heliosheath. The spacecraft's instruments acted as sensitive antennae, tuning into the faint whispers of this cosmic boundary layer. Each measurement, each subtle change in temperature, density, or magnetic field direction added another piece to the puzzle. It was like assembling a vast and intricate mosaic, slowly revealing the hidden structure of our solar system's outer reaches. And with each new discovery, Voyager pushed the boundaries of our knowledge further outwards, preparing us for what lay beyond, a truly interstellar realm where the laws of physics are governed by forces far grander than anything we experience at home. It's a place shaped not by our sun, but by the collective energy and matter of an entire galaxy. And as Voyager continues its journey, it carries with it a small piece of ourselves, venturing ever deeper into the cosmic unknown. Our sun, but by the collective energy and matter of an entire galaxy. And as Voyager continues its journey, it carries with it a small piece of ourselves, venturing ever deeper into the cosmic unknown. For decades, scientists theorized about what lay beyond the bubble created by our star's influence, a region where the solar wind, that constant stream of charged particles emanating from the sun, would finally give way to the true interstellar medium. It wasn't simply a matter of leaving behind the familiar warmth and light, but crossing a boundary defined not by distance alone, but by a fundamental shift in environment. To imagine it is to picture a ship sailing beyond the last headland, out of sheltered waters, and into the vastness of the open ocean. Except this ocean isn't filled with water, but with plasma, magnetic fields, and cosmic rays. The transition wasn't sudden, of course. It unfolded over years, even decades, as Voyager slowly navigated a complex region known as the Heliopause, the outermost layer of the sun's influence. As Voyager approached this boundary, instruments began to detect subtle changes, hints that it was entering a new realm. One of the first clues came from measurements of plasma density and temperature. For years, Voyager had been surrounded by relatively warm, sparse plasma originating from our sun. But as it pushed further outward, the concentration of these particles began to drop dramatically, replaced by the colder, denser plasma characteristic of interstellar space. It was like feeling a chill in the air, a subtle but unmistakable sign that you were leaving behind familiar territory. Confirming this transition, however, proved surprisingly difficult. The heliopause isn't a sharp line. It's more akin to a turbulent mixing zone where solar wind and interstellar plasma collide and interact, disentangling. These overlapping signals required meticulous analysis and sophisticated modeling. Scientists had to account for variations in the solar wind itself, as well as the ever-present background noise of cosmic radiation. It was like trying to hear a whisper in a hurricane, demanding extraordinary sensitivity and careful interpretation. Voyager's instruments, the plasma spectrometer, the low-energy charged particle instrument, and others worked tirelessly gathering data, each piece contributing to the growing puzzle. Another key indicator of crossing into interstellar space came from changes in cosmic ray energy levels. Cosmic rays are high-energy particles that travel throughout the galaxy, originating from distant supernova and other cataclysmic events. The sun's magnetic field normally deflects a significant portion of these particles, shielding our solar system. As Voyager moved beyond the heliopause, this shield weakened, resulting in a noticeable increase in the number of cosmic rays bombarding its instruments. This wasn't necessarily dangerous to the spacecraft. It was designed to withstand harsh radiation, but it provided another crucial confirmation that it had indeed entered interstellar space. It revealed just how much our sun protects us from the raw energy of the cosmos, an invisible embrace we often take for granted. But perhaps one of the most intriguing discoveries came in the form of a sound, or rather a whistle. In late 2013, scientists analyzing data from Voyager's plasma wave science instrument detected a unique signal, a sustained hum that differed significantly from anything they had heard before. This whistle, as it became known, was believed to be caused by interstellar plasma waves resonating with the spacecraft's antenna. It wasn't a sound audible to human ears without special processing. It existed at incredibly low frequencies, but its detection represented something profoundly new. Voyager wasn't just sensing a different environment, it was hearing it, intercepting the faint song of interstellar space itself. Imagine the implications. For the first time, we had a direct acoustic window into the vastness between stars, a subtle but compelling reminder that even in the seemingly empty vacuum of space, there is constant activity, flowing energy, and hidden complexity. To scientists, it wasn't just a sound, but a fingerprint, an identifying signature of the interstellar medium itself. Analyzing this unique whistle offered valuable insights into the density and composition of the surrounding plasma, helping to refine our understanding of this mysterious region. It was a testament to Voyager's enduring sensitivity, its ability to detect even the faintest whispers from across the cosmic gulf. And as Voyager traveled deeper still, these signals continued to evolve, painting an increasingly detailed picture of the interstellar environment. Scientists discovered that the magnetic field in interstellar space wasn't uniform. It had a distinct direction and strength, hinting at the underlying structure of our galactic neighborhood. They also found evidence for turbulence, swirling eddies of plasma, driven by interactions with nearby stars, confirming theoretical predictions about the dynamic nature of the interstellar medium. Each observation was like adding another brushstroke to a vast cosmic canvas, gradually revealing a landscape previously hidden from view. Voyager's journey into interstellar space wasn't merely an engineering triumph. It was a scientific revolution. It fundamentally altered our understanding of the boundary between our sun and the rest of the galaxy, demonstrating that this transition zone is far more complex and dynamic than anyone had imagined. The data gathered by Voyager continues to be analyzed today, revealing new insights into the nature of interstellar space and its relationship to our own solar system. And while Voyager's power supply will eventually dwindle, the radioisotope thermoelectric generators are slowly losing their capacity. Its legacy will endure for generations to come, a testament to human curiosity, ingenuity, and our unyielding quest to explore the cosmos. It remains a beacon of exploration, quietly reporting back its findings from the edge of known space, a little piece of Earth carried on the solar wind, whispering stories of what lies beyond. A cosmos, it remains a beacon of exploration, quietly reporting back its findings from the edge of known space, a little piece of Earth carried on the solar wind, whispering stories of what lies beyond. And as Voyager journeys further still, something fundamental begins to shift in our relationship with this tiny emissary. The very experience of communication itself alters, stretching and bending with the vastness it traverses. Imagine holding a conversation across an ever-widening ocean. Each response takes longer to arrive. Each question feels increasingly distant from its answer. This is the reality for mission control as Voyager approaches and then crosses the 1 light day mark. For nearly half a century, we've enjoyed near instantaneous contact with our robotic explorer, sending commands and receiving data with only minutes of delay. But once Voyager surpasses that boundary, roughly 16 billion miles from Earth, or about 173 times the distance between the Earth and the Sun, Every signal becomes an exercise in patience, a careful negotiation with the fundamental speed limit of the universe, the light itself, traveling at approximately 186,000 miles per second, now requires a full day to make the round trip. Think about that for a moment. A command sent from Earth will take 12 hours to reach Voyager, and another 12 hours for any response to travel back. A simple request, a course correction, even just a status update, becomes a 24-hour conversation. Calculating these distances and delays is deceptively complex. Of course, it isn't simply multiplying distance by speed. The relative motion of both Earth and Voyager must be accounted for, as does the subtle curvature of space itself over such immense scales, though that effect remains minimal at this range. But the core principle remains. Light has a finite speed, and as distances grow, so too does the time it takes for information to travel between us and our distant probe. To give you a sense of scale, Alpha Centauri, the closest star system to our own, lies 4.24 light-years away. Communicating with Voyager at 1 light day is hardly comparable, but it offers a tangible preview of the extreme delays that would define any future interstellar communication attempts. This extended round-trip time has profound implications for how mission control operates. Real-time commands, the kind used during the early phases of the mission to make quick adjustments or troubleshoot unexpected problems, become impossible. There's simply no way to react instantly to changing conditions or unforeseen events. Instead, a new strategy emerges: pre-planning and automation. Mission controllers essentially create detailed sequences of instructions, carefully crafted playlists for Voyager to execute autonomously over extended periods. These playlists are uploaded days, even weeks in advance, taking into account predicted scenarios and potential contingencies. It's a bit like composing a letter rather than having a phone call. You must anticipate every possible question or problem, providing detailed instructions and solutions within the message itself, knowing there's no opportunity for clarification until the reply arrives. A very long time later, the team spends countless hours simulating Voyager's responses to different stimuli, running models and testing algorithms to ensure that the probe can handle a wide range of situations without direct human intervention. This reliance on automated systems isn't new, of course. Even in the early days of the mission, Voyager possessed a degree of autonomy, the ability to respond to certain events without waiting for instructions from Earth. But as the communication delays increase, that autonomy becomes absolutely critical. Voyager has been designed with layered redundancies and fail-safes. If it encounters an unexpected problem, it's programmed to attempt self-diagnosis and corrective action before resorting to emergency protocols, or if those don't work, entering a safe mode while awaiting instructions. Consider the simple act of pointing Voyager's instruments at a specific target in deep space. In the past, mission control could fine-tune the probe's orientation in real time, precisely adjusting its trajectory to capture the desired data. Now, it requires sending a series of commands hours beforehand, hoping that the target will still be in the correct position. When Voyager finally executes the maneuver, the team relies heavily on onboard gyroscopes and star trackers, sophisticated sensors that allow Voyager to maintain its orientation without external guidance. These instruments are constantly monitoring the probe's attitude, making micro-adjustments as needed to keep it pointed in the right direction. The data itself also undergoes a transformation. Rather than receiving a continuous stream of information, mission control now receives it in large chunks, accumulated over many hours or even days. This requires new methods of analysis, sifting through vast amounts of data to identify patterns and anomalies. It's like assembling a puzzle with missing pieces. You have to rely on incomplete information and careful deduction to get the full picture. There's an undeniable sense of letting go that accompanies this shift in communication, a subtle acknowledgement that Voyager is becoming truly independent, venturing into regions where our direct control diminishes. It's a poignant reminder of the vast distances that separate us from even our closest robotic explorers. But within that sense of distance lies a profound beauty, a testament to human ingenuity and the enduring spirit of exploration. We built this instrument, sent it on its journey, and now, as it sails further into the interstellar sea, we trust in its ability to navigate the unknown, guided by the principles of science and the echoes of our distant commands. The silence between signals isn't an absence of connection. It's a measure of Voyager's achievement, a quiet testament to its resilience, and a humbling glimpse at the scale of everything beyond. Humbling glimpse at the scale of everything beyond. Consider for a moment the simple act of looking up on a clear night. The stars you see, those ancient beacons reaching across vast gulfs of space, appear to twinkle with an immediacy that belies their true distance. But light itself isn't instantaneous. It travels, and its journey defines our perception of everything beyond our world. As Voyager 1 presses onward, leaving the immediate neighborhood of our sun behind, it approaches a milestone defined by this very principle. One light day, imagine stretching out your hand, then extending it further and further still. Now imagine that extension continuing for an entire day at the fastest speed possible in the universe, nearly 6 trillion miles. That's roughly what constitutes one light day. The distance light travels in 24 hours. To express this in a way familiar to those charting Voyager's course, it translates to approximately 173 astronomical units. 1 astronomical unit, remember, is the average distance between Earth and our Sun, a convenient yardstick for measuring the solar system's immensity. Reaching 173 of these units means Voyager has ventured far beyond even the outermost planets, well past Pluto, and into the realm where sunlight dwindles to a faint glow, replaced by the diffuse radiance of interstellar space. For nearly half a century, we have been sending signals outwards, questions posed into the darkness, carried on radio waves at the speed of light, and for almost as long, we've received responses, telemetry data detailing Voyager's health, its trajectory, and the conditions surrounding it. But that two-way conversation is about to subtly shift as Voyager crosses this one light day threshold. A fundamental change occurs in how we communicate with our distant emissary. Think of shouting across a field. The sound waves reach your friend almost instantly, allowing for a quick back and forth exchange. Now imagine that field stretching into an ocean, then a continent, and finally encompassing a significant portion of the planet itself. Each shout, each message sent, takes longer to travel, and the response takes just as long to return. When Voyager reaches one light day from Earth on November 18th, 2026, every command we send will take an entire day to reach it, and then another full day for its signal, its status report, its acknowledgement of our instructions to find its way back home. A 48-hour round trip for the simplest request, a deliberate cadence imposed by the very fabric of space and time. It's easy to lose sight of this delay in our modern world, accustomed as we are to near instantaneous communication across continents. The internet grants us an illusion of immediate connection, but Voyager's voyage reminds us that the universe operates on a different timescale, one measured not in seconds or minutes, but in days, years, and even millennia. This isn't a technological limitation so much as it is an inherent property of existence itself. The speed of light is constant, a universal law governing the flow of information. And while we've developed remarkable technologies to amplify signals and compensate for distance, those laws remain immutable. It offers an almost meditative perspective. each interaction with Voyager becomes a carefully considered exchange, not a rapid-fire dialogue. To truly grasp this shift in communication, consider even more distant targets. Alpha Centauri, the closest star system to our own, lies approximately 4.25 light years away, sending a message to any potential inhabitants. There would require over 4 years for each transmission and another 4 years to receive a reply. An 8-year conversation at the absolute minimum. Voyager, though still comparatively close in cosmic terms, is taking its first step toward these even more profound delays. As it travels further into interstellar space, the communication window will widen, stretching potentially to decades or even centuries for future probes venturing towards other star systems. The very notion of real-time control becomes impossible. We must essentially entrust our emissaries to operate autonomously with pre-programmed instructions and a robust capacity for self-diagnosis and correction. This is not a loss, but rather an evolution in how we explore the cosmos. It demands patience, foresight, and a willingness to accept that some journeys are measured not by immediate results, but by long-term discoveries, a slow unfolding of knowledge over generations. Voyager's light day milestone isn't simply about distance. It's about embracing these new realities of interstellar exploration, acknowledging the inherent delays, and learning to communicate with the universe on its own terms. It's a testament to our ambition, not just to reach for the stars, but to listen patiently for their response, even if that response takes days or years to arrive. And in that listening, we find a deeper understanding of ourselves, our place in the vastness of space, and the interconnectedness of all things. It becomes less about controlling a distant probe and more about establishing a lasting legacy, a message carried on light itself, traveling onward into the infinite currents of the cosmos. All things. It becomes less about controlling a distant probe and more about establishing a lasting legacy, a message carried on light itself, traveling onward into the infinite currents of the cosmos. And then, quietly, almost unnoticed, amidst the larger rhythms of earthly life, it happened. November 18th, 2026, a date that will not likely find its way onto calendars or into grand celebrations, and yet a moment marking a profound shift in our relationship with the universe around us. On that day, Voyager 1 became the first human-made object to reach a distance of 1 light day from Earth. The confirmation came, as these things often do now, not with trumpets and fanfare, but with a carefully worded press release from NASA jet propulsion laboratory. It detailed years of meticulous data analysis, the painstaking accumulation of signals received across billions of miles, each photon a whisper from the edge of our solar system. The numbers had been building for some time. Of course, the steady increase in flight time for even the simplest commands, the ever-widening gulf between here and there. But it wasn't until late in 2026 that the team felt confident enough to declare the milestone officially achieved. They weren't looking at a sudden flash on a screen or a dramatic leap in readings. Instead, they were examining subtle changes in signal round-trip time, the delay between sending a command and receiving confirmation of its execution. As Voyager 1 pushed beyond that critical threshold, that delay stretched to 24 hours, a full day for a message to travel out and back, a quiet but unmistakable measure of the sheer scale of space. Imagine it. You speak, and half a day later, your words finally arrive. Half a day for an acknowledgement to return. The implications are both humbling and exhilarating for those involved in the Voyager mission, many of whom had dedicated decades of their careers to this endeavor. It wasn't necessarily a moment of boisterous joy. Decades spent navigating intricate orbital mechanics, solving unforeseen engineering challenges, and coaxing every last bit of life from aging systems tends to foster a more subdued sense of accomplishment. There was certainly relief, an immense satisfaction in knowing that the probe had exceeded all expectations, continuing its journey far beyond its original design parameters. But mostly, it was a feeling of quiet awe, a recognition that they were witnessing something truly unique, something that would likely not be repeated for generations to come. The team had been tracking this crossing for years, refining their calculations. With each new data point, they'd built complex models to account for the subtle effects of gravitational lensing and the ever-changing background radiation of interstellar space. The confirmation wasn't simply a matter of seeing the distance exceed 3 billion miles, roughly 173 astronomical units. If you prefer that measure, it was about verifying the accuracy of their models, confirming that their understanding of the cosmos held true at these extreme distances. What's truly remarkable is how far Voyager 1 has traveled on so little power. The probe relies on a radioisotope thermoelectric generator, or RTG, which converts the heat from decaying plutonium into electricity. That source was designed to last at least 20 years, nearly 50 years after launch. However, it continues to provide enough energy for essential systems to function. Though with dwindling output, every watt is carefully managed. Every instrument prioritized based on scientific value and power consumption. It's a testament to the ingenuity of the engineers who built Voyager 1, their ability to create a spacecraft that not only survived, but thrived in the harsh environment of interstellar space. Think about that for a moment. A machine launched in 1977, long before many of us were born, still transmitting data from beyond the edge of our sun's influence, powered by the slow decay of elements forged in distant stars. It's an extraordinary feat of engineering and a poignant reminder of humanity's capacity for long-term vision. The signal is incredibly faint now, barely above the noise floor, but it continues to arrive on Earth, carrying with it a wealth of information about the interstellar medium, the tenuous gas and dust that fills the space between stars. Beyond this boundary, beyond one light day, every communication becomes an exercise in patience. Every command sent from Earth takes 48 hours to reach Voyager 1 and another 48 hours for a response to return. It's a delay that forces you to reconsider what it means to control something across such vast distances. You're no longer guiding the probe in real time. You're essentially sending out instructions into the darkness and hoping that they are received and understood. It's as though Voyager 1 has crossed an invisible threshold, stepping from a realm of active control into a realm of quiet observation. It continues to gather data, but increasingly, its purpose is becoming less about scientific discovery and more about symbolic endurance, a testament to our reach, our curiosity, and our unyielding desire to explore the unknown. And in that endeavor, it serves as a powerful preview of what future interstellar missions might entail. Consider the vastness of space beyond even this milestone. One light day is an immense distance, yes, but it's just a tiny fraction of the journey to Alpha Centauri, our nearest stellar neighbor, 4.24 light-years away. At Voyager 1's current speed, it would take over 70,000 years to reach that system. It places this achievement into perspective, doesn't it? This isn't about reaching a destination. It is about sustaining a signal, maintaining a presence, a fragile beacon of human ingenuity drifting through the void. The spacecraft itself will eventually fall silent, its power source depleted, its instruments failing. But even then, Voyager 1 will continue to travel onward, carrying with it the golden record, a carefully curated collection of sounds and images meant to represent life on Earth. It's a message in a bottle cast into the cosmic ocean, a hopeful gesture towards any potential civilizations that may someday encounter it. And so it journeys on, becoming less about where it is going, and more about what it represents as it travels through the darkness, a testament to our place within the grand tapestry of the universe. And so it journeys on, becoming less about where it is going and more about what it represents as it travels through the darkness, a testament to our place within the grand tapestry of the universe. But even testaments fade with time, and Voyager's continuing story isn't simply one of distance traveled, but also of connection maintained, a delicate balance against the relentless march of physics. Consider for a moment the sheer improbability of this ongoing conversation stretched across the gulf between stars. Think about how it began nearly half a century ago, powered by ingenuity and a slowly dwindling source of warmth. Voyager isn't fueled by solar panels, bathed in sunlight, like many of its robotic cousins closer to home. Instead, it relies on a radioisotope thermoelectric generator, an RTG, which converts the heat produced by the natural decay of plutonium-238 directly into electricity. It was a clever solution for a mission venturing so far from the sun that solar power would become impractical. But it's important to remember that decay is precisely what's happening. The plutonium isn't creating energy from nothing. It's gradually transforming into other elements, and with each transformation, less heat is released. Each year since launch has brought a subtle decrease in the available power, a slow dimming of Voyager's internal fire. When Voyager was first launched in 1977, its RTG produced roughly 470 watts of electricity, enough to comfortably run all the spacecraft's instruments and transmitters. Now, after nearly 5 decades, that output has fallen to less than 420 and continues to decrease by approximately 3 to 4 watts per year. It's a gradual loss, almost imperceptible in daily terms, but cumulatively significant over such vast timescales. Imagine trying to power your home with a battery, steadily losing its charge. The appliances still function, perhaps, but with less vibrancy, requiring careful management of resources. That's precisely what mission controllers at NASA Jet Propulsion Laboratory have been doing for years, carefully managing Voyager's instruments, cycling them on and off strategically to conserve energy. Some instruments were already switched off in the late 1990s, early 2000s, to extend the lifespan of others. Decisions made not out of failure, but out of necessity, prioritizing which data could be returned given declining resources. The high-gain antenna, crucial for maintaining that faint radio link back to Earth, remains a priority, as does the main transmitter. But even those systems require careful calibration and adjustments to maximize their efficiency. You might wonder if there's any way to replenish Voyager's power source, to send a cosmic refueling station hurtling through interstellar space. It's not really feasible. The amount of plutonium-238 needed would be immense, and the logistics of such a mission are currently beyond our capabilities. Instead, engineers have focused on squeezing every last drop of energy from the existing system. They've developed advanced software algorithms to optimize power usage, carefully balancing the needs of each instrument against the dwindling supply. They are managing heat dissipation, too, ensuring that critical components don't overheat, while minimizing the amount of electricity needed for cooling. As Voyager approaches this one light-day milestone in late November of 2026, we will find ourselves at a turning point. The signal will grow even fainter, taking nearly 34 hours for each message to reach us, and another 34 for a reply. Every command sent becomes a commitment made far into the future, a quiet acknowledgement of cosmic distances, a delay representing over 17 billion miles. This isn't a failure, though. It's simply the natural consequence of traveling so incredibly far. It is a reminder that communication across interstellar space isn't instantaneous, but a measured exchange carried on the back of light itself. The team at JPL are actively exploring strategies for extending Voyager's mission even further, anticipating that around 2030 they may need to make difficult choices about which instruments to keep operational, potentially leaving only one or two functioning to ensure some level of data return. They're working to streamline the software, eliminate redundant processes, and improve the efficiency of the remaining systems. Digital austerity for a spacecraft adrift in the darkness, and yet, even as its signal fades and its power diminishes, Voyager remains an extraordinary ambassador from Earth. It carries with it a golden record, a message in a bottle launched into the cosmos, intended to convey the story of our world to any intelligent life that might one day encounter it. That record isn't just about information. It's about intention, a deliberate act of reaching out across the vastness, expressing our hope for connection and understanding. Perhaps, in some distant future, an alien civilization will intercept Voyager's signal, decipher its message, and learn something about the world that sent it on this incredible journey. Or perhaps not. The likelihood is small, but the act of sending the message itself is what truly matters, a testament to our curiosity, our ambition, and our enduring desire to explore the universe and share our story with whatever lies beyond. It's a reminder that even as things end, new beginnings are possible, and that, in the grand scheme of cosmic time, every journey, no matter how long or short, leaves its mark on the endless night. And so, Voyager drifts further still, carrying not just instruments, but a fragment of ourselves into the vastness between the stars. To think that a signal, traveling at the ultimate speed limit, will take nearly 2 full days to reach it and return. It's a humbling perspective, isn't it? A quiet echo of distance against the backdrop of everything we know and all that remains unknown. Imagine looking back from that far shore, seeing our world as just another star, faint but enduring, a pale blue point suspended in an infinite dark. Thank you for spending this time among the stars with me. If you enjoyed the journey, a gentle like and a subscribe help more quiet dreamers find their way here. Until next time, rest well and keep wondering about the cosmos. Good night.